Now we discuss one of the most important application of transmission line, and that is what is called the impedance matching. We have seen that if the impedance is equal to the characteristic impedance, then there is no reflection on transmission line and there is a maximum power transfer. However, as we saw, it is not always possible to design the circuits which will have input or output impedance which is equal to the characteristic impedance. What we then require is a module which can convert this input or output impedance of a circuit to the characteristic impedance. This module is what is called the matching unit or a matching transformer. So, essentially we want to introduce some kind of a module in between what is called an impedance matching device, on one side of which we want to see the impedance which is equal to the characteristic impedance Z naught. Other side is the impedance which is some impedance which is not equal to Z naught. Through the impedance transformation unit, when impedance is seen, that should appear like Z naught. So, we are certainly using the impedance transformation characteristics of transmission line inside this unit, what is called the matching unit. But once we come outside this matching unit, then the impedance always appears equal to Z naught. So, beyond this point on the left, if I see, the impedance always will be equal to the characteristic impedance. Since the matching unit is used only for transforming the impedances, ideally this unit should not consume any power. So, we should see the impedance from the left side of this unit equal to the characteristic impedance. This unit should be completely lossless and the power should be finally delivered to the load which is not equal to the characteristic impedance. So, today we discuss the various methods by which the impedances can be matched to the characteristic impedances by using a lossless device in between. Let us take first a very simple problem, and that is, let us say I want to match a real impedance to the real characteristic impedance. We will still follow that the transmission line which we are using is a low loss or a lossless transmission line. So, the characteristic impedance of this line is almost real. That means, we want to match now an impedance to a real impedance which is the characteristic impedance. So, let us say, to start with, let me assume that I want to match a real impedance to the characteristic impedance which is also real. So, I am looking for a device which can match a real impedance to a real impedance. What is the application of this? You will find there are many applications where this will be needed. One is a simple case. Suppose I am having a module where the impedance is a resistive impedance. This impedance, when seen through the transforming device, it should appear like this impedance which is equal to characteristic impedance, one possibility. Other possibility, I have two different resistances which are to be matched by using some kind of a transforming device in between. So, let us say I have some electronic circuit on this side, some electronic circuit on this side, and both of them do not have the same value. And if they do not have the same value, if I directly connect them, there is a mismatch. So, there is no maximum power transfer from this circuit to this circuit. So, I can introduce some device in between which will transform R2 to appear like R1 when seen from this side, and will appear R1 to appear like R2 when seen from the right side. So, both sides the circuit see as if they are matched to the conjugate loads, and there is a maximum power transfer. The third and important case would be that, let us say, suppose I have two long transmission lines which are to be connected. A joint has to be formed between these transmission lines. If the length of the transmission line is very large, then the input impedance of this will appear almost the characteristic impedance of the transmission line. If I have to make a joint between these, and if I just make a straight joint, this cable or this transmission line will see as if it is connected to an impedance of Z02, which is the characteristic impedance of this line. This line will see as if it is connected to an impedance of Z01, which is characteristic impedance of this line, and there will be reflection on both sides of this junction on these two transmission lines. So, what we want to introduce a transforming device in between, so that this impedance Z02 appears like Z01 when seen from this side, and when seen from right side the Z01 appears like Z02. So, from both sides you see as if the line is terminated in its characteristic impedance, and then there is no reflection on either side of the transmission line. So, matching a resistive impedance to the characteristic impedance has many practical applications. Let us see how do we do that now. Firstly, we will note that if you are having a resistive impedance and it has to be matched to the resistive impedance, the impedance seen from the left side should be the resistance. Let us go to our Smith chart and ask this question, that if I have impedance which is a resistance, then how much should I go on a transmission line so that the impedance always appears like resistance? So, what we are now saying is, let us introduce another section of transmission line in between, which we call as the impedance transformer, and let us say it has some characteristic impedance given by Z0x, which is different than the characteristic impedance of this line to which the resistive impedance is to be matched. So, there are two parameters to be found out for the transformer. One is what should be the value of this characteristic impedance Z0x, and what should be the length of this transmission line which is introduced in between the resistive load and the characteristic impedance. So, if I go to the Smith chart and if I have an impedance which is resistive impedance, we know the resistive impedance lie on the horizontal axis on the Smith chart. So, if I take any impedance which is greater than Z0, it will lie on the right hand side of the center. If the impedance is less than Z0, it will lie on the left side of the center, but all purely resistive impedances will lie on the horizontal axis. Now, if I move now on the transformer, which is another section of transmission line, to see a resistance I have to move on a constant VSWR circle passing through a resistance, so that I reached again to the horizontal line, because I want to see the transformed impedance again a real impedance, so that it becomes equal to the characteristic impedance Z0. So, there are two possibilities: either I move a distance of lambda by 4, or I will move a distance of lambda by 2, so that I see the impedance again as resistive impedance. So, my original impedance is resistance. By transforming by a distance of lambda by 4 or lambda by 2, I will again see an impedance which is the resistive impedance. However, we know that the impedance characteristics of transmission line repeat every lambda by 2. That means, if I move by a distance of lambda by 2, I will see the same impedance. So, I do not get any advantage. Whatever impedance I am seeing, the impedance to be matched R, the same impedance now appears after a distance of lambda by 2. So, this possibility is of not any use, because it transforms the impedance to itself. So, only possibility that I see a resistive impedance after transforming to a resistive value is that I move by a distance of lambda by 4. So, if I take this transforming device and move by a distance of lambda by 4 on this, so this is my transforming unit, to this side of which is connected a resistance R, which is to be matched to the characteristic impedance Z0, which is also real, and this distance now has to be lambda by 4, because then only this impedance R will be transformed to another resistive value. We also know the property of transmission line, that every distance of lambda by 4, the normalized impedance inverts itself. So, the normalized impedance seen at this point here, that is R divided by Z0x, because the characteristic impedance of this transforming line is Z0x. So, the impedance seen here is R divided by Z0x. This is the normalized impedance which you will see here. This normalized impedance inverts itself after a distance of lambda by 4. So, if I see the impedance here, the normalized value of this impedance will be inverse of this. So, it is Z0x divided by R. So, the absolute impedance which I am going to see here is multiplying this normalized impedance by the characteristic impedance of the transforming unit. So, that is Z0x multiplied by Z0x divided by R. That is absolute impedance I am going to see at this location. This impedance for matching should be equal to Z0. So, now we have got a condition that for the transforming unit the Z0 should be equal to Z0x square divided by R, or in other words the Z0x, which is the characteristic impedance of the transforming unit, that is the geometric mean of the two resistances to be matched. So, this is now in general true that if I have two resistances to be matched, R1, R2, or one of the resistance R and the characteristic impedance Z0, or two cables which are having characteristic impedances Z01 and Z02, the transforming section must have a characteristic impedance which is the geometric mean of these two resistances, and the length of this section should be quarter wavelength or lambda by 4. So, that means if I introduce a section of lambda by 4 length whose characteristic impedance is geometric mean of the two resistances which are to be matched, then from both sides you will see a match. The R will appear like Z0 when seen from this side. One can verify that Z0 I can transform by this on the other side, and that will appear like R. So, on this side you see a match, this side you see a match, and since we are introducing this section of a transmission line which is completely lossless, there is now a complete power transfer from the transmission line to the resistance R. So, without losing any power now, we achieved the impedance seen on the left of this box equal to characteristic impedance. And as we know, once the impedance becomes equal to characteristic impedance, every point on the left of this line will always be equal to characteristic impedance. So, this technique is what is called the quarter wavelength transformer technique. This is one of the very important devices which is used even in lumped form to match the two resistive impedances. One can now wonder at this point, is this method only useful for matching two resistive impedances? In general, I may have an impedance which is complex, and then I would like to match that complex impedance to the characteristic impedance which is real. Is it possible to use the quarter wavelength transformer technique for matching a complex impedance to a real impedance? In first look, one might say it does not seem to be possible, because what we got here is transforming a real impedance to a real impedance. The whole argument was using the Smith chart that the impedances are lying on the real axis and I want to transform them again back to the real axis. So, this is possible only for the real impedances. However, if you think little carefully, you will see that is not true, because any complex impedance can be transformed into a real impedance by moving along the length of a transmission line. Whenever there is a voltage maximum or voltage minimum, you see the impedance to be purely real. That means, if we introduce some section of a transmission line, same transmission line with characteristic impedance Z0, then the impedance seen at this end of the transforming box, that will be a real quantity if the length transform the impedance in such a way that there is a voltage maximum or voltage minimum at this end. So, it is possible to match a complex impedance R plus jx. So, this impedance is R plus jx. From here, the principle is exactly same, that if I get an impedance here which is real, then I can transform by using quarter wave transformer the impedance to equal to Z0. However, to make the impedance real at this point, I introduce a section of a transmission line which is having some characteristic impedance Z01, it could as well be Z0, and transform this impedance R plus jx to a value which is a real value. So, there are two things. One is what should be the length of this line, and what is the value of this impedance which you see at this location. This we can do again very simply by using Smith chart. So, firstly we take the Smith chart Now, here I have drawn the Smith chart in very few circles on that. So, this is the Smith chart, which is the outermost circle, this is the unity circle, and these are the x equal to 1 circles. Let us say my r plus jx in normalized form is denoted by this point P. As we have seen earlier, the first step is to draw a constant VSWR circle through this. So, I draw this circle, which is the constant VSWR circle. So, as I move on the transmission line of this characteristic impedance Z01, I move on this constant VSWR circle. Keep in mind, since I am using the impedance for this line as Z01, the normalized impedance is with respect to this impedance Z01. So, normalization of this R plus Jx is to be carried out with respect to this characteristic impedance. Once I get this, then as we move towards the generator, I move on the constant VSWR circle. If I reach to this point, which is the rightmost point T on the constant VSWR circle, then the impedance here will be real and its value will be the VSWR. So, the normalized impedance, which is the resistive value, is equal to the VSWR on this transmission line. So, if I know the VSWR from here, then the impedance seen at this point is known. So, let us say the VSWR, which is created on this, is given by some rho. So, the value corresponding to this point T will be Z01, which is the characteristic impedance of this line, multiplied by the VSWR. So, the impedance at this location, which is R max, that will be equal to the VSWR. Similarly, if I go to a point here S, which gives you the minimum resistance, that its value will be the R min, and that will be equal to Z01 divided by the VSWR. So, if I move by a distance from here to here towards the generator, since I am moving clockwise, this distance will correspond to this length L, and the value at this will be Z01 into VSWR. So, if I take L equal to L max, then the impedance which I am going to see, which is denoted here by Z prime, this impedance will be equal to Z01 into the VSWR rho on this line. On the other hand, if I take L as L min, which is the length up to the minimum point, which is this. So, from here all the way clockwise up to this location, if I take that length for L, is L, then the transform impedance Z prime will be Z01 divided by the VSWR. Once I know this impedance, then the impedance of the transformer will be geometric mean of this impedance and the characteristic impedance Z0. So, I have two solutions. If I take the transformed impedance here, which is Z01 times rho, then I get some characteristic impedance value for a transformer. If I take this value, I will get another characteristic impedance value for a transformer. So, this problem has two solutions depending upon what length you choose for transforming this impedance to a real value. Any solution is acceptable depending upon whether you want a length shorter or larger, and whether the transform impedance which you get can give you a realizable transforming line. One may choose one solution over the other, but theoretically there is no difference between the two solutions, and both the solutions are equally acceptable. So, this technique, the quarter wavelength transforming technique, can match the impedances even from complex impedance to a real impedance. So, this technique is used in practice in many applications. However, one would immediately note this technique has a biggest drawback, and that is you require a unique characteristic impedance for this transforming device. Later on we will see that the characteristic impedance of a transmission line, it depends upon the physical dimensions of the transmission line. That means for every impedance matching we require a unique physical structure created for transmission line, so that I get precise value of this characteristic impedance. This is not a very desirable feature, because in practice we do not get the transmission lines whose characteristic impedance can be varied very easily. Normally we get the cables or the transmission line which have standard characteristic impedances. For example, if I take coaxial cables, the characteristic impedances are 50 ohms or 75 ohms. If I take parallel wire transmission lines, their characteristic impedances would be 300 ohms, 600 ohm or something like that. So realizing any arbitrary value of characteristic impedance is not very easy. So though principally any complex impedance can be matched to the characteristic impedance by using quarter wavelength transformer, in practice it finds difficulty, because you will not be able to realize a transmission line, or it will be difficult to get a separate transmission line for each impedance matching which is to be carried out in the circuit. So the next option which we now look for is, can I use the standard transmission line which are available, and making use of those transmission lines, can I match a complex impedance to the real impedance? And this approach is what is called the stub matching technique. So this is what is called stub matching technique. Now stub is a section of a transmission line which is short circuited or open circuited, connected to the main transmission line either in series or parallel. So to the main transmission line, if I make a connection of another similar transmission line which is either open circuited or closed circuited at the other end, then this appended line to the main line is what is called the stub. And by using now the sections of the stub at proper location on the main transmission line, it is possible to match a complex impedance to the characteristic impedance of the line. Note here, what we have realized in this is, we do not require a unique characteristic impedance for each matching. The transmission line characteristic impedance is same. Only we want to change now the location and the length of this appended line to the main line. There are two possibilities for doing matching by using this technique. I can use only one appended line to the main line, and then that technique we call as a single stub matching technique. If I have two appended lines to the main line, then that technique is called the double stub matching technique. So let us see first the single stub matching technique, and as the name suggests, we have the problem as follows now. This is my main line which has a characteristic impedance Z0. This line is connected to an impedance Z, which finally is to be matched to the characteristic impedance Z0. Let us say we connect a line in parallel to this line, which is what is called the stub, and let us say the stub is short circuited. So in this case we have connected the stub in parallel with the main transmission line, whose length is Ls and whose characteristic impedance is same as Z0, and this stub is connected to the main line at a distance L1 from the impedance to be matched. So now idea is that in this section here you have the standing waves because of the reflection from Z. The impedance is transformed from this point to this point, so you get a reflected signal which comes from here. So the reflected signal is going to come from here also because this is short circuited. So let us see the first the problem, how the energy will start flowing. The voltage wave comes here, it is two paths, one towards this stub, one towards the load. The voltage wave reaches to the load, part of the energy gets reflected from here, so you have a reflected wave from here. the voltage wave which has gone toward the short circuit of the stub is fully reflected, and when the two reflected wave reach at this point, if we make sure that these two waves are equal in amplitude and opposite in phase, they will cancel each other at this location. So, the reflected wave coming from the stub and coming from the load, if they can cancel each other, there is no net reflection beyond this point, or in other words, if there is no reflection on this point, this part of the line, the impedance is always equal to the characteristic impedance. Same thing we can say in different words from impedance point of view. If I take this impedance and transform the impedance at this point, in general it will have a resistive and reactive part. The stub, which is short circuited, will always have a reactive part. If I make sure that the parallel combination of the impedances which you see here, the reactive part cancel, you see the impedance seen from here is purely resistive, and if that resistive part is equal to the characteristic impedance, I achieved the matching. So, the problems are now as follows: find this length L1 such that when the impedance is transformed here, its resistive part becomes equal to the characteristic impedance and it has some reactive part. Choose the length of the stub in such a way that the reactive part cancels this reactive part. So, the resistive part is equal to now the characteristic impedance beyond this point. Doing this exercise analytically is rather tedious. However, if you use the Smith chart for carrying out this operation, then this exercise turns out to be extremely simple. So, this technique, since we are using only one stub for matching the impedance to the characteristic impedance, we call this technique is the single stub matching technique. Now, since we are doing here the operation of parallel connection of these two lines, let us say the problem now is defined in terms of admittances, because the handling parallel connection will be easy in terms of the parallel connections. So, let us say I write down the impedance in terms of the admittance. So, I take 1 over z, and let us say that quantity is given by y, which is equal to 1 upon z. So, I have the admittance at this location, and I find out the characteristic admittance, I find out the normalized admittance at this location. So, every operation which I am doing now is in terms of the admittances. Let us see how do we solve this problem by using Smith chart. The problem is as straightforward. Let us say we are having some point which is the impedance which is to be matched. Let us say this point is given by P, this impedance. So, this location here is the normalized admittance, and let me denote this normalized admittance y bar is G plus JB. So, G is the normalized conductance, B is the normalized susceptance for this impedance which is to be matched. So, since I am now doing the calculation for admittances, I am using the Smith chart as the admittance Smith chart. So, here the Smith chart is admittance. I mark this point G plus JB, which is the impedance to be matched. So, this point P is G plus JB. The first step, as we do, we draw the constant VSWR circle passing through this point. So, this circle is the constant VSWR circle. Now, we can note that when we move on this circle, that means when we move on the transmission line towards the generator, my first task is to make the real part of the admittance equal to the characteristic admittance, or the normalized real part should be equal to 1. So, when I move on this circle, I find that whenever this circle intersects this G equal to 1 circle, conductive part has become equal to 1. So, at this location B, I have the conductance G normalized has become equal to 1. Similarly, if I take a point D, its normalized conductance has become equal to 1. So, by moving a distance corresponding to this or moving a distance corresponding to this, I can find out now what would be the reactive part at this location, because the resistive part or the conductive part of this has become equal to 1. Okay. Now, let us do this exercise. So, let me take this Smith chart and do that. So, this is my Smith chart. Let us say we saw this point marked is P, which is G plus JB. I draw a constant conductance circle passing through this point on this. This is the unity circle. So, this point here or this point here, at this location the conductive part of the admittance has become equal to 1. So, either I can move by a distance corresponding to this, so that its conductive part has become equal to 1, or I move by a distance which is equal to from here to this, so that its conductive part becomes equal to 1. Any of the solutions are acceptable. Let us say I take a solution that I move by a distance on the Smith chart, which is this. Then this length is nothing but L1 in this figure. So, I have moved by a distance L1, so that here now the conductive part become equal to 1. Now, so at this location the value of the admittance is 1 plus, let us say, some J B prime. So, if I just without a stub, if I move on this line and if I see towards the load, I will see now here an admittance which will be 1 plus J B prime. So, if I see here, just here, this will be 1 plus J B prime. If I have to cancel now this admittance reactive part J B prime, the stub which I have connected in parallel must have an susceptance which is minus J B prime. So, if I take looking this way, the susceptance must give me a value of minus J B prime. So, when the two are connected in parallel, 1 plus J B prime added with minus J B prime, the J B prime cancels, and I will see beyond this point and normalized admittance which will be equal to 1 plus J 0. Now, corresponding to this J B prime, now I want to find out what is the point which is minus J B prime. If I have to realize that reactance on the by using the section of transmission line, that is easy. If I take a mirror image of that and pass through the reactance circle which is passing through this point, that is the point which is outermost point on the Smith chart, this point, that corresponds to minus J B prime. So, note what we have done. This location is 1 plus J B prime. I take a mirror image of that on the constant VSWR circle, find the constant reactance circle or constant susceptance circle passing through this, go to the outermost point which represents minus J B point. Now, to realize this susceptance from the section of a transmission line, as we have seen earlier, this susceptance can be realized by length such that if I move from this point away from the generator, I must reach to the short circuit point. Remember, now we are using the Smith chart as the admittance Smith chart. So, this point is the short circuit point. And this point is the open circuit point. So, to realize this reactance, if I move from this point away from the generator till I reach to the short circuit point. That gives me the length of the stub which is to be connected in parallel. So, this length from here to here, that is nothing but your the length Ls, which is the length of the stub. So, you see the finding the length of the stub and the location, if you use the Smith chart, is extremely simple. We mark the unknown admittance which is to be matched, move on the constant VSWR circle up to a point when it intersects the G equal to 1 circle. At that location, the value of the admittance is 1 plus JB prime. Take the mirror image of this point on the constant VSWR circle, find the constant susceptance circle passing through that point, go to the outermost point on the Smith chart on that circle, find the length of the stub from that susceptance to the short circuit point, which is the rightmost point on the Smith chart. So, by doing this simple exercise, we can find the location and the length of the stub. The similar exercise can be done if you are having impedances, and if the stub is connected in series, you use the Smith chart as the impedance Smith chart, and beyond that point the exercise is exactly identical. In this case, we have taken the 1 plus JB prime point, which is this point. We have taken this point also. In that case, we have to move at distance L1, which will correspond to from this point up to this vector, this length, and the value here will be 1 minus JB prime. So, you will require a stub reactance should be plus JB prime, which will correspond to the point which is mirror image of this. So, the length of the stub would be corresponding to all the way from here to here. So, again the problem has two solutions depending upon what value of 1 plus JB prime you choose. If you choose this, I get the length of the stub which is this, and the location of the stub which is given by that. If I choose this point all the way from here to here, the location of the stub and the length of the stub would correspond to mirror image of this point measured all the way up to the short circuit point. So, single stub matching technique is an extremely useful technique in matching any impedance to the characteristic impedance of the line. So, note here now that as in the previous case of quarter wave transformer, we are matching here any unknown impedance to the characteristic impedance, but we do not require any special transmission line now. The same transmission line sections are used. So, without requiring any special type of transmission line, we can achieve the impedance matching between any complex impedance with the characteristic impedance. This technique, however, has a small drawback, and that is the location of this stub depends upon the impedance to be matched. Many times it is possible that you can connect the stub to the line. It is easy to vary the length of the stub, but it is not always possible to really change the location of the stub, because once the stub is connected to the line, it is not easy to move the location of the stub. Take a simple case. Suppose I am having a coaxial cable kind of structure. For connecting the stub to the coaxial cable, I have to drill the hole in the outer conductor of the cable, make joint with the center conductor and outer conductor. Once that joint is made, then by having some kind of a shorting plunger inside the coaxial structure, I can change the length of the stub easily. But for changing the location of the stub, I have to desolder or remove the joint, again drill the hole somewhere else in the coaxial cable, again make a joint, which is an extremely tedious process. So, though the single stub matching technique can match all possible loads, it has this drawback that for every load to be matched, the location of the stub has to be changed, which every time may not be that easy. So, we go to the second technique, what is called the double stub matching technique, where the matching between the loads is realized by changing only the lengths of the stub but the location of the stub remains fixed. So, the second technique, which is what is called the double stub matching technique, is a technique which can match a load to the characteristic impedance without changing the location of the stub. So, the location of the first stub L1 is fixed, the separation between these two stubs is fixed, and by changing just the lengths of these two LS1 and LS2, we do the matching of the load to the characteristic impedance. Let us see how do we do that. So, first let us work out how the impedance variation would take place. So, this point here we get an impedance which is 1 plus J0, which is the match impedance, which is nothing but a combination of the impedance which we would see here 1 plus JB2 minus JB2 comes from this stub. So, you see the impedance which is equal to 1 plus J0. So, the whole matching requires that at this location C, the impedance seen just beyond this point C should be 1 plus JB2. That means the impedance which is seen here at this location should be such that when we move a distance of this from B to C, the impedance should fall on the G equal to 1 circle. This transformation now is the one which has to be worked out on the Smith chart. If you do analytically, again the problem is extremely tedious. With the help of Smith chart, this transformation can be done very easily, and then one can work out the lengths of and the locations of the stubs. The separation between the stubs is generally taken as 3 lambda by 8. Why do we choose 3 lambda by 8? We will see little later, but at the moment let us say that the separation between the stubs was fixed, which was 3 lambda by 8, and the location of the first stub also was fixed, that was L1. So, the impedance seen at this location here just before this, which is G1 plus JB prime. So, the original admittance was G plus JB. After transformation by a distance of L1, the admittance seen is G1 plus JB prime, which when is combined with the susceptance minus JB1, you get a admittance here which is G1 plus JB1, which is when transformed appears like an admittance 1 plus JB2, which is when cancelled with the susceptance of this stub minus JB2, you see a net admittance which is 1 plus J0. So, how do we do this transformation? By using Smith chart. Firstly, if this point has to be 1 plus JB2, this point has to lie on a circle which is a rotated version of G equal to 1 circle by 3 lambda by 8 distance, which corresponds to 270 degrees away from the generator. So, first thing what we do in this double stub matching, the figure has many circles. This is the G equal to 1 circle in the Smith chart. If I rotate the entire circle by 270 degrees, which is 3 lambda by 8, away from the generator, that means in the anti-clockwise direction, I get a rotated G equal to 1 circle, which is this circle. So, this circle here is rotated G equal to 1 circle. So, if this location B, if I can bring this admittance to lie on this circle somehow, then by moving along the transmission line, that means along a constant VSWR circle, after a distance of 3 lambda by 8, the point will come on G equal to 1 circle. And once the point comes on G equal to 1 circle, then I know how to match, because that is exactly same as what we have done in the single stub matching technique. So now the idea is as follows. I have an admittance here which is G plus JB, which is denoted by this point A. This is the length L1 to which the admittance is transformed, that is denoted by this point B, which is G1 plus JB prime. Now at this location we are adding a stub, that means we are changing only the reactive part of the admittance. That means from here I must move on a constant conductance circle, because the conductance value is not changed by this stub. So I move on the constant conductance circle passing through B till I reach to a location on the rotated G equal to 1 circle. So this is my constant conductance circle. This is the point which is your B plus point. So just beyond the stub, this admittance what you see, that is this admittance. So from point B I move on the constant conductance circle till I come to the rotated G equal to 1 circle. Beyond this point then I am moving on the transmission line. So I must move on constant VSWR circle. So I draw a constant VSWR circle passing through this B plus point, and I move on this by 3 lambda by 8 or 278 degrees towards the generator, that means in clockwise direction. Obviously this point will fall on G equal to 1 circle, which is this point. That point is 1 plus JB2 point, which is this location. Once I get this, I have to cancel JB2, so I take mirror image of this JB2 and find out which is the mirror image of this point passing through this point, and find out or what should be the length of this stub, so that it will give me susceptance of minus JB2, which is same as what we have done in the single stub matching. So let me again repeat how do we do that. First mark the normalized admittance on the chart, move by a distance L1 on a constant VSWR circle passing through A to come to a point B, then move on a constant conductance circle till you reach to the rotated G equal to 1 circle, draw a constant VSWR circle passing through this point B, move on the constant VSWR circle in the clockwise direction till you come to G equal to 1 circle, find the reactive component plus JB2, mark minus JB2 point on the Smith chart as we have done in single stub matching, find the length of the second stub moving from that minus JB2 point to the short circuit point in the anti-clockwise direction. How do we find out the length of the first stub? That length should give me a susceptance which brings the point from this to this. So if I know the susceptance at this point, the difference of these two, this minus this, because the conductance is same at these 2 points, difference of these two susceptances are to be provided by stub 1. I can take this difference, mark on the Smith chart, the outermost value, again measure in the clockwise direction. That should be the length which should give me a susceptance equal to the difference of the susceptances at these 2 points. So the difference is this, and if I move from this point away from the generator up to the short circuit point, I get a length which is the length of the first stub. So now by doing this I can get the length of this stub and the length of this stub. Location of the stub is fixed now. So when the load impedance or admittance varies, just by changing the length of these stubs I can achieve the matching. So this technique takes away the limitation of the single stub matching which has taken away the limitation of the quarter wave transformer. So, for a variable impedance or admittance environment, the double stub matching technique is a extremely useful technique. However, this is a small problem, and that is the whole process of matching is possible provided by moving a constant conductance circle. I can come on the unit G equal to 1 circle. If by this movement on constant conductance circle I can't reach on rotated G equal to 1 circle, the matching is not possible. Now, if you know the nature of constant G circle, they are one within another. So, this is the G equal to some circle, the higher value of G equal to some circle will be inside this, inside this, inside this, and so on. So, it is possible that if the point admittance at point B at this location, this one, if it lies here inside this region, then by moving along the constant conductance circle, I will never be able to come on rotated G equal to 1 circle. And if I can't come here, then the impedance after transforming cannot come on the G equal to 1 circle here, and the matching is not possible. So, what that means is, if this impedance G1 plus JB prime, if it lies in this region, what is called the forbidden region, then the impedance matching is not possible. The grace, however, lies in the fact this is not the load impedance, it is this impedance which should not lie in the forbidden region. The impedance which we want to match can lie in the forbidden region, but this impedance, transformed impedance after distance L1, that should be out of forbidden region. So, by choosing proper value of L1 need not be very precisely, just as a step, there is a possibility that this point can be taken out of the forbidden region. So, as such, the double stub matching technique has a small limitation, that it cannot match those impedances whose transformed value after L1 lies in this forbidden region. However, this thing has been taken away by introducing a concept simple, which is the 3 stub matching, and that is, if I take this load, what we can do is, instead of using two stubs, let me use 3 stubs. The distance between all of them is 3 lambda by 8, this is 3 lambda by 8, and this is some value L1. What I can do is, if because of these 2 stubs, the matching is again double stub, but if the matching is done with these 2 stubs, I can make this open circuit by checking this length equal to quarter wavelength. If I find that by choosing these 2 stubs, the transform impedance lies in the forbidden region, I can disconnect this stub and make use of these 2 stubs. So, depending upon whether the transform impedance lies in the forbidden region or not, either I can make use of this 2 stubs or these 2 stubs. So, the final solution in the impedance matching is the 3 stubs technique, that by using this now, all possible impedances can be matched without moving the location of the stubs on transmission line. So, that completes the discussion of the impedance matching of unknown impedance to the characteristic impedance of transmission line.